Okay, hello everyone. Welcome back to the Algorithmic Seminar. So it's my great pleasure today to introduce our speaker for today, Katie Everett. Katie is a research engineer at Google DeepMind, where she focuses on understanding and improving training dynamics and parameterization in large-scale neural networks. And in addition to DeepMind, Katie is also a PhD candidate at MIT. And yeah, thank you so much for being here today. And floor is all yours.
Yeah, thank you so much for the invitation. I'm very excited to give this talk. So yeah, my name's Katie Everett. I'm at Google DeepMind and MIT, and this talk is going to be about this paper that appeared at ICML last summer, scaling exponents across parameterizations and optimizers, which deals with the kind of parameterization theory of width scaling. And this is joint work with a number of different collaborators, and in particular, Lachao, Jaehoon, and Jeffrey were the other core contributors on this project. So first, I'm going to start with some very high-level motivation for why we care about parameterization in the first place. And this motivation has three kind of primary components to it. So the first is that we exist now in this train once era of very large models. And this is an empirically motivated situation, right? So we know from these early papers on scaling laws that the performance of large language models improves as a power law in the number of parameters and the number of tokens. And this kind of improvement is like very predictable as a power law across a very large number of orders of magnitude of compute. And what this motivates is that if we are trying to train good models and we have a particular compute budget to use for our entire experimentation process and then training the models, what it suggests that we should do is that we should save the majority of our compute for a very, very large model, just because if large models are better, we want to train kind of the largest single big model possible. And what this means is that we're going to spend a smaller fraction of our total compute budget on experiments in small and medium-sized models. And we need to use those experiments on these smaller and medium-sized models to make all of the decisions about this one giant training run before we start that run. And so we're going to need to be able to make all of our architecture and hyperparameter decisions about a giant training run based on experiments that are done at much smaller scale than that actual training run. So the second big component of the motivation is that it turns out that if we want to scale transformers up in a way that's compute optimal, it's not just like a single dimension. You could imagine a universe where we had some kind of like architecture that everyone was using, where when you want to make it bigger, you just like make the architecture have more layers or something like that. But in reality, what happens with transformers, right, is that we know empirically that we actually want to co-scale at least the width, the depth, the number of training tokens, the batch size, context length, bookup size, right? Every time we do empirical studies, we find out that it's important to have co-scaling relationships between these things. So we have all of these different scaling dimensions. And then it also turns out that every time we change any of these scaling dimensions, it influences what the optimal hyperparameters, like the learning rate and momentum and such for the optimizer are. And all of these scaling dimensions, they don't just independently affect the optimal hyperparameters, but all of these scaling dimensions interact and affect the optimal hyperparameters. And what this gives us is a hyperparameter search space that has like at least a dozen very highly interacting dimensions. And then the third component of the motivation requires a kind of small calculation that you can do on with some pencil and paper. But I will kind of tell you the key points of this. So if you consider just like a MLP with one hidden layer, and you're going to train it with SGD, and you assume that you're going to use a global learning rate. So like every parameter in the network is updated with the same learning rate. And you make some like pretty reasonable assumptions about this. What you find is that if you just kind of write down what the scale of each quantity, like the parameters and activations and the gradients in the network look like, and you figure out what learning rate would make each of the layers have the updates stay kind of a similar scale to the parameters. We'll get in later in the talk, we'll get into kind of more details about like this style of calculation. But what you see is that you have like between different layers, for example, between the hidden layer and the readout layer, the learning rate that that layer would kind of want the network to be trained with has a different scaling exponent with respect to the width. So the hidden layer kind of wants the learning rate to scale like 1 over the square root of width, whereas the readout layer wants it to scale like 1 over width. And what this means is if you're training a model using a global learning rate, you kind of, as you scale the width, you kind of have to follow one of these exponents, because kind of large enough size, only the exponent will matter. And you kind of have two bad choices. Either like your readout layer is going to blow up because the learning rate is too big for that layer, or your hidden layer is eventually going to be kind of dead and the updates will be trivial to the hidden layer. If you decide that you're going to make the readout layer happy and then have a learning rate that's too small for your hidden layer. So this kind of calculation in an MLP is just like an example of what I would call a scaling mismatch. So you have different parts of the network where you have different kind of optimal exponents in some important quantity. And the thing is if you have ever just like trained an MLP at like a reasonable width, you probably didn't see this kind of behavior where you noticed that something was either dead or blowing up inside of your network. Because what can happen is that at a small enough scale, these exponents are like, the contribution of the exponents doesn't necessarily outweigh all of the other terms contributing here. And so, yeah, you can have these kind of scaling mismatches that you don't notice until you scale up beyond a certain size, when suddenly these exponents become so dominant that you see some kind of bad behavior. And so this can lead to kind of a sudden training instability or sudden like performance degradation at a certain scale that you wouldn't have predicted if you were only kind of trying to extrapolate from empirical understanding at smaller sizes. So given all three of these pieces of motivation, we're very strongly motivated to not strictly take an empirical perspective on scaling, but also to develop a theory for scaling. So the kind of three major components of this theory that we want is that we want to understand how small experiments should inform larger experiments. And this gets into this kind of notion of hyperparameter transfer. We have this basically a dimensionality reduction problem where every dimension that we can understand theoretically reduces one of the dimensions in this like highly interacting hyperparameter search space. And then in addition, we really want to have reliable extrapolation. So if there's going to be a phase transition from one of these like scaling mismatches or some kind of numerical instability, we want to know about it at a scale before it actually occurs. And having theory to do this can at least kind of point us in the right direction of where we should be looking for these kinds of scaling mismatches and understanding them before we are like training some really expensive large model and like something goes wrong in the middle of training. So, okay, now I'll switch from motivation into more kind of technical background specifically about parameterization. So the kind of informal definition that I use for parameterization in a neural network is that it's going to be a prescription for the exponents of a particular set of quantities with respect to some set of scaling dimensions. In this paper, we're going to specifically focus on width as the scaling dimension, but you could imagine you could have a parameterization that's taking into consideration like co-scaling width and depth and batch size or something like that. But the important thing here is that what we're going to prescribe is specifically the exponents. The way that parameterizations are usually implemented in practice has this particular functional form that has like a very special property that lets us do hyperparameter transfer. So if you're thinking about how I'm going to specify some part of the parameterization, like the learning rate is going to be part of our parameterization, what we're going to have is that we're going to set things up so that that value is always equal to some constant multiplier that's going to be determined empirically, multiplied by some scaling dimension that's raised to an exponent that's been derived theoretically. So the important part here, right, is that we're choosing this functional form because it like works well in practice and it's going to enable hyperparameter transfer. Because what's going to happen is that we're going to have some theoretical reasons why we think that a certain exponent is the correct thing. And then what we're going to do is at a small size, we know like the value of the scaling dimension at that small size. We know the value of the exponent, and we can sweep the empirical constant at a small size. And we're doing it at small size, so it's much cheaper to like do this sweep of the constant. But then because we have this like theoretically derived exponent, we can reuse the empirical constant across all model sizes, right? Because we basically have this like scaling dimension to the exponent term that tells us how this value needs to change as we change the size of the model. And this is kind of the like functional form that enables like mu-p style hyperparameter transfer. So, okay, more specifically about width scaling parameterization. So the way that we're going to define a width scaling parameterization is that it's going to be the prescription for the exponents in each layer of the model. So these things I can have like a separate prescription for these three quantities in the embedding layer versus the hidden layers or readout layer. We're always going to treat all of the hidden layers the same way. So there's always going to be like three types of layers. But if you really wanted to, you could like change things like layer by layer so that all the hidden layers operated differently. You just have like a very hard search problem to solve. But the three quantities that we're going to prescribe here are going to be the variance of the initialization. There are these quantities we call parameter multipliers that get multiplied during the like forwards pass of the network that I'll define kind of more concretely in a couple of slides. And then the learning rate. So if you think about it, right, the initialization variance and the parameter multipliers are kind of part of the initialization of the network. And then the learning rate, right, is something that's going to be specific to the optimizer that's just going to affect things like during the actual training process. So, okay, I won't go into too much detail of this, but just there's quite a bit of existing theory along like the mu-p papers line of work. There's like a set of assumptions that are typical in that kind of theory. One thing is that we're always looking at this single epoch case. So our train loss and our test loss are kind of like equivalent to each other because we've never like the next training token is from the same distribution as a test token, and we haven't seen either one of them. So they're kind of equivalent in this like single epoch or streaming setting. And then the existing theory makes a bunch of assumptions about like the batch size and the depth and the training steps and vocab size all being constant with respect to width. Although we do know that in practice, right, there's like empirically motivated and sort of also in some cases like theoretically motivated reasons for large models to not have these quantities scale with width. So just know that we're making these kind of simplifying assumptions in a lot of the theory that most of like the scaling dimensions other than width are going to be held constant. So, okay, now we'll get a bit more into the specific kind of theoretical setup in our paper. And a lot of this early setup is following the like proposals from the mu-p papers. And I'll make clear in a few slides like where we start deviating from that setup. Yeah, okay, so in terms of the problem formulation, right, we're going to make a choice in how we set up our theoretical framework here, where we're going to decide that we care about the scale of kind of a typical entry in a matrix. And we're going to define this kind of typical entry notion using like a root mean squared norm. So if you think of if you took a matrix where every entry had the same value, right, then the root mean squared is going to just be that value. And know that like there's other choices that you could make of the norm here that give other kind of interesting theoretical perspectives. Like some work by Jeremy Bernstein and others has perspectives about like spectral norms or other choices of norms. But for the purpose of this paper, we're taking this root mean squared norm perspective. The other thing that we're doing is that we're considering the large width limit. And so we always care about the exponents on the width. We're going to track we're basically going to track these large width exponents of the root mean squared, and we're going to drop kind of all of the other terms. And so like throughout this talk, you're going to hear me say that there's a particular quantity has like a certain scale. And so what we're going to do is we're just going to like, this is just saying in math, right? We're going to take the RMS norm, and then we're going to take the log so that the exponent is the dominant term, and then we're just going to look at the large width limit. The second component of this problem formulation, kind of also following mu-p, is that there are these different notions of like how we want the quantities in the network to behave. So the one that we're going to focus on most in this talk is this notion of stability, which basically we're training these neural networks on like finite precision machines. And so we don't want quantities to get too big or too small. And so this notion of stability, we're going to define as saying that the activations in the network have to stay exactly constant scale with respect to width both at initialization and during training. And then the logits, we're going to allow them to be smaller than constant scale, but they're not allowed to exceed constant scale, right? So this is basically just like preventing everything in the network from like growing larger as the width grows large, to prevent things from blowing up numerically. So, okay, this like notion of stability, right? We can define it with saying that like, okay, these particular quantities have to stay a constant scale. But then we have this problem that we need to solve, which is we need to make decisions about what initialization we're going to use and then what learning rates we're going to use in every layer. And so first we're going to go through kind of, I'll walk through a calculation about like setting up the initialization. And then we're going to have this larger kind of more complicated problem to solve, which is what is the maximum stable learning rate that I can use in each layer of the network while still like solving for all of these constraints. Okay, so I apologize, this is going to get a bit notation heavy, but I'm going to try to focus on kind of the key intuitions here. And you can follow the paper if you are interested in like the more details. But here, okay, we're just going to consider an MLP. You can focus on the model defined over on this right-hand side. So what we're going to have is, let me explain these. Okay, so we have these weight matrices, right, like defined as normal. We have N is the width, like the width of the network that we're actually going to think about scaling. D is the input and output dimensionality, which we'll think of as being fixed. We have nonlinearities drawn here, but for the purpose of this whole discussion, just pretend those are an identity function, so you can just like drop those nonlinearities. And then, okay, so let me talk about these parameter multipliers that I mentioned before. So what we have here, right, we have this activation Z1, right? We have some input data X. We have the normal trainable parameters inside of the matrix W1. And then we also have this extra constant term, which we're writing out as N, which is the width to negative A1. So this, right, we're just, this A1 is controlling this parameter multiplier, right, which is just some constant. And the only difference between having like this constant times W1 versus just having those constants be part of the initialization in W1, right, is that there's like an equivalence class or like a symmetry here where pulling some kind of like pulling a multiplicative factor outside of the trainable part of the parameters, it does like you can rescale things so that you don't change the forward pass at all. But what it does is, because when we do the chain rule kind of goes through this parameter multiplier on the way back to getting the gradients with respect to W1. It's just going to rescale by that constant term, like what the gradients are with respect to the parameters. And so if you, in this symmetry, you then need to like correct your learning rate basically to account for the fact that you made your gradients bigger or smaller by this particular term. So yeah, we just have this MLP with these parameter multipliers. And then, right, we define the width for a transformer, the like model dim, like the width of the MLPs. We're kind of ignoring the attention block in at least this part of the discussion. Yeah, okay, so this is the kind of core model. And then for the parameterization, right, as I already said, this like these values A sub L are going to specify these parameter multipliers. B sub L is going to tell us the, okay, these are all, it's a little annoying that there are negative signs in this notation, but it like saves you from having a bunch of negative signs later. So all of these are going to be negative exponents, where negative B is going to be like the exponent of the standard deviation for the parameter initialization. And then negative C is going to be the exponent of the learning rate. And so this like the parameterizations for each layer are going to be specified by these quantities, A sub L, B sub L, and C sub L. Okay, so we now are going to do our first calculation kind of keeping track of the scales of things inside of the network. So in the embedding layer, right, we have this, we're just trying to figure out, we know from how we defined things, what the scales are of everything on the left-hand side of this first row. So we know we have n to the negative A1, we have this exponent. We know that W1 scales or grows like n to the negative B1, right? And then we were making this assumption that the data is always going to be a constant scale. And so this is like n to the 0. And what we're trying to do is figure out what is the scale of this activation Z1. And in this case, it's like quite straightforward because when we're doing this matrix multiplication, where the kind of the like interior dimension in this like matrix vector multiplication between W1 and X is the input dimension that we're treating like a constant. We just get that like Z1 is going to scale like these three terms multiplied together. And so we kind of like know directly what the exponent of Z1 will look like. For the hidden layer is a little bit trickier because we now have a matrix multiplication between WL and ZL minus 1. We're going to assume that we have been like using the stability constraints from the embedding layer kind of like incrementally going through the network, so that we are always going to enforce that the activations coming into a layer are already assumed to be constant scale. But what we have now is a slightly trickier problem where we have a matrix multiplication where we have like random Gaussian entries in WL, and we're multiplying by the activation ZL minus 1. And here we get this extra square root n term contributed because we're taking kind of dot products. I'll explain this in a bit more detail in a couple slides, but we're kind of taking dot products and we're summing a bunch of random Gaussian variables. And just from like central limit theorem scaling, we have this like extra contributed square root n term. But what this does is this shows you kind of like the style of calculation that you would do if you want to figure out how big the activations are at initialization, like as you go through the network. So then from what we just did, right, if you, I guess it's a bit hard to like remember across the slides, but we just figured out what the scale of Z1 was, right? And it was like a negative A1 minus B1 would be the scale of Z1. So we just enforce this constraint that equals 0, which is just enforcing basically that Z1 is going to scale like n to the 0 so that it stays constant. So that came from that first part of the last slide. And then the next like stability constraint, right, comes from the same calculation, right? But that square root n term introduces this like 1/2. So now we have this constraint that AL plus BL has to equal exactly 1/2 for all of the hidden layers. And then if you remember, we said that for the logits, we're going to allow them to be smaller than constant scale. They're just not allowed to exceed constant scale. And that's why we get an inequality with this 1/2 in the readout layer. And so this is like, you now understand how these stability at initialization constraints show up. And if you remember before in our parameterization, right, we have A, B, and C, where A and B are describing parts of the initialization, and C is only describing like what happens once we actually start training. So you notice these stability constraints are just like linear constraints that only take A and B into account. And it doesn't actually matter what learning rate we have when we're just talking about this stability at initialization. So these are kind of the 4 most well-known parameterizations, just writing out like what the values of A and B are going to equal. And the question then we have is, okay, what is the maximum stable learning rate that we can use in each one of these parameterizations in every layer? So, okay, this is where things start to get a bit more interesting. So during training, we need to now figure out the same thing, but we need to do like very similar math where we, right, we need to do very similar math, but we now need to, in addition to calculating just how big the activations are, we're going to need to calculate how big all of the gradients are, and then based on the learning rates, the gradients plus the learning rates will tell us how big the updates are, and that will let us figure out stability constraints throughout training. Okay, so now this has all been background. I realize it's taking a bit. I'll try to speed up. But in terms of the theoretical contributions in our paper, so there's this assumption that's used in prior work, especially in UP, that when you are considering these how big every time you have like a multiplication between your activations and your parameters, you have to answer this question about how much alignment there is between your activations and your parameters. And I'll give you a quick kind of intuition about what this notion of alignment means. So, okay, you already know from like high school geometry class or whenever you first learned geometry that if you want to know how big the dot product is of two vectors, right, you need to know three things. You need to know how big is A, how big is B, and then you also need to know the angle between A and B. And there's a very similar kind of like phenomenon going on when you multiply your activations and your parameters. Because if you think about a matrix multiplication, every entry is just the dot product of some row with some column. And so the size of these entries is also just going to depend on like the angle or the alignment between like the rows in your parameter matrix and the columns in your activation matrix. And so you can actually like build all of the intuition that you need just thinking about the vector case. And the kind of like cliff notes on if you do this calculation, you basically just like can see this in the vector case, and you just like center your vectors and apply the central limit theorem or like law of large numbers. And what you see is that if you have the situation that you have at initialization, where there's no reason for your activations or like your data distribution and your parameters to be correlated or aligned with each other, then you get this scaling where you have, when you multiply a matrix A times a matrix B, the scale of that product matrix, right, is going to be the scale of A times the scale of B times a square root n term, where n is like the dimension in the matrix multiplication that you're contracting over. But if you imagine the case where like you have the rows in your parameters and the columns in your activations are pointing in exactly the same direction, then you get that the scale, rather than growing like square root n when you do this matrix multiplication, it can grow by up to a full factor of n. So the key kind of assumption that's made in prior work that differs from what we do is that they assume that in at initialization, you always have this no alignment case where you have this square root n contribution. But then as soon as you take your first training step, you could have kind of up to perfect alignment. And they assume what is kind of like ends up being a conservative assumption that you have up to like an n contribution, which is, I'm saying it's conservative because if you assume there's more alignment, then you need to make the learning rates smaller to counteract this. And so you're being kind of conservative and having smaller learning rates to ensure that things don't blow up. So, okay, I'll give a brief summary of our theoretical contributions. So what we do is investigate and kind of reframe this problem of this alignment assumption. So the first thing that we do is that there's this expansion that happens every time you try to figure out how big your activations are, where you end up with these like four terms between either your initial or your kind of updates to your parameters and activations. And we give the alignment contribution from each of these individual terms its own name. And then in addition, we go empirically investigate like how much alignment is actually showing up in practice. And so we define this metric, which is basically answering this question of how much, so it's really answering the question of in the first row here, right, there's going to be this multiplication between W plus delta W. That whole quantity times the Z plus delta Z term, there's whatever like alignment shows up there tells us some number that's probably going to be between like 1/2 and 1 is going to tell us like what exponent we need to add when we're figuring out the size of these exponents. So we go and define this metric first, and then we measure this during training on a bunch of different parameterizations and model sizes. And what we see are these interesting patterns. Like the most important takeaway here is that the alignment is intermediate, right? It's in between 0.5 and 1. So 1 is actually like a assumption that's too conservative relative to what we're seeing in practice. But also, right, it's like very dynamic. It changes a lot during training. And then there's also some kind of specific patterns where like the readout layer in MUP and mean field spikes up much higher than in standard and NDK. And we have some hypotheses about why that is in the paper. I will let people take a look at prior work kind of on their own time. But yeah, so in the paper, we investigate then kind of the like space of different assumptions that you could make about alignment, right? We have the different alignment variables, and then you can drop in different values for whatever assumptions you want to make for each of these values. But there's a particularly important thing, which is that there's this particular assumption in the readout layer in the MUP papers that assumes that this omega term, which shows up on the parameter initialization times the update in the activations. And there's a if you make kind of the most conservative possible assumption for that particular alignment variable in that particular layer, that is actually the assumption that is required to derive the uniqueness of mu p. And so what we do is we kind of like zoom out and we first derive everything in a way that's general to these assumptions about the alignment. And in particular, we like relax this particular alignment variable's assumption on that particular layer in the network. And what that does is it gives us actually parameterizations that we can then run experiments with that are considered stable under our like slightly relaxed assumptions that were just excluded from the set of parameterizations that mu-p looked at because they were considered unstable by the theory once you like have this particular assumption. So then, okay, we derive the learning rate constraints in terms of A and B and these like three different alignment variables. This is what it ends up looking. So in this first section, right, this is what we already saw for stability at initialization. And then for Atom, it's like optimizer specific, right, for what constraints you need on the activations and the logits to keep stability during training. And then we do this in the paper again for SGD and add effector. And then, yeah, so now we can finally do what we were hoping to do the whole time, which is to solve for the maximum stable learning rates in every layer. So this gives us like a space of like all of the different parameterizations and layer-wise prescriptions that we can use. So the really cool result that comes from this is that, right, we made this like more general theoretical space of parameterizations to look at by like very slightly relaxing one of the alignment assumptions. And what happens is that we can get kind of mu-p style hyperparameter transfer on all four of these different parameterizations with like a little asterisk. The mean field one has like some quite like numerical stabilities that I'll talk a little bit more about in a couple slides. But yeah, so the way to kind of parse this plot is in this top row of plots, what we're doing is we're plotting the eval loss on the y-axis against the base learning rate, so that kind of like constant multiplier in the learning rate. And what we would see if we had perfect like mu-p style hyperparameter transfer across width is that each of these curves is a different model size, and we would see these orange dots like perfectly line up vertically because we'd use the same like learning rate multiplier at every model size. And so we can see that it's like pretty close to vertical on all of the parameterizations. And then the bottom panels here basically are just like taking all of these orange dots and then replotting them where we're plotting now the learning rate versus the model dim. And then I just like fit a power law through these so that we can look at the actual exponent of that power law. And if we have perfect hyperparameter transfer, right, we should get an exponent that's almost exactly 0, which is what we see, right? These are all like quite close to perfect hyperparameter transfer, except for like a little issue with mean field. So then the other nice result here is that, so as we, right, when we looked at this like more general space of parameterizations, and we have all four of these different parameterizations now have this hyperparameter transfer property, we also actually see better performance from this standard parameterization like per layer variant that was like kind of previously excluded from the space of parameterizations that people were looking at. And the performance gain here is actually pretty significant. So if you can actually see that the like 15 billion parameter standard parameterization model actually outperforms the 27 billion parameter mu-p model just by like using this kind of like theoretically motivated per layer version of standard parameterization. So then, okay, another interesting result here is that if you remember at the very beginning when I was talking about like the functional form for the hyperparameter transfer, right, we have these like constant multipliers on the learning rate. And there's a few different ways that we can define these constant multipliers. So this functional form, again here, right, if you look at what I'm calling these default constants, this beta sub n is, you can think of as like the empirical constant that we're sweeping. And then we have this like width over base width. You can kind of ignore the base width thing. It's just to kind of like rescale stuff. But that's basically our scaling dimension raised to this negative c sub l is like, again, like our theoretically motivated exponent. So you can decide to sweep this constant in a bunch of different ways. So I think the typical thing to do would be to do a single sweep on beta, uh, like a one-dimensional sweep, and find the optimal beta n for like all of the different layers of the network, just using kind of the same value of beta n. And that's what we started with. But we found actually that it's extremely important to do a sweep that's like specific to the layer type. So we introduced this like extra term I'm calling gamma here. So then we do a three-dimensional sweep where we find basically the best constant multiplier for the embedding times hidden times readout layer space. And then we can do this at a very small scale, and then reuse all three of these constants and do hyperparameter transfer of this like three tuple of constants. And it turns out actually that this tuning step is extremely important for the performance of the models. So like we actually initially didn't do this, and then I was saying that like the theory was not giving us good results on like all the different parameterizations. And after trying this like strategy of tuning at this three-dimensional space at small scale and then transferring it across scale, then right, we got like significant improvements in performance across multiple parameterizations. Okay, I want to leave a bit of time for discussion, but there's one more interesting section of results in the paper. So there's this notion of epsilon underflow in Atom. And the tensor programs 4B paper already had kind of proposed that you should be thinking about epsilon as part of your parameterization. I've been talking about, right, there's like three parts of the parameterization, but there's actually this fourth part in Atom, right, which is epsilon. And the key kind of intuition here, right, is I just wrote down like the Atom update rule here. And if you notice, right, we have this like additive epsilon term in the denominator in the Atom update. But what actually happens is that we can figure out how the gradients are going to scale with width with the same kind of style of calculations that we've been doing. And it turns out that these gradients are getting smaller with respect to the width. And if you think that epsilon is going to be a like constant value, if your gradients are getting smaller as the width gets bigger, eventually, if you get to a big enough scale, this will actually like your gradients will get smaller than epsilon, and this update starts to look almost like SGD again, where epsilon is kind of like dominating over this like gradient second moment term. So it turns out that this actually happens in practice if you're using a typical value of epsilon that's near like 1e negative 8 or 1e negative 9. And so we do a set of experiments with epsilon where we try a few different things. We have like the baseline kind of a typical constant. We try a smaller constant. We use this epsilon parameterization that's kind of like the theoretically principled thing to do, but it's like quite complicated to implement. And then we also propose this like new variant of Atom that we call Atom arctan2, where rather than having an epsilon term to kind of keep numerical stability, we do like an arctan2 function so that we can have this like very like small number division in a numerically stable way. Yeah, so what we find is actually that particularly in mean field parameterization, it's particularly sensitive to epsilon. All three of these kind of interventions on epsilon significantly improve the performance. And there's another like very nice result that kind of like wraps up a lot of things in the paper here, which is that I mentioned briefly that there's this notion of kind of symmetries with these parameter multipliers. And if you look in the paper, we talk a bit more about these equivalence classes, but basically like under these equivalence relations, standard and NTK parameterizations are kind of, they're theoretically equivalent, but this equivalence is assuming infinite precision. So they're theoretically equivalent, and then mu-p and mean field are also theoretically equivalent to each other. But before you fix this epsilon underflow issue, right, if you look at the performance of all four of these different things, you have four distinct curves, and you're like, wait, I was supposed to have two equivalence classes, but I actually have like four totally different performing models. But after you fix this issue with epsilon underflow, right, you see these like four curves collapsing almost into two different classes. So I think this is like very like nice that you can show really that if you fix something that's like a precision related issue, that you now actually get this theoretically predicted behavior where you have these two equivalence classes reflected in these actual curves. Yeah, okay, so that is all I have for content. I'm happy to open it up for questions and discussion.